This video is for Math 63, and this is for our week 8 assignment on scientific notation. And so first off, there are going to be three. I've got three handouts for this. One is just on writing scientific notation. One is on calculating in scientific notation. And one is doing word problems that involve scientific notation. So I'll go over the problems from all of these, and hopefully that will be helpful. So the first idea behind scientific notation is, what is it? So what it is generally a number between 1 and less than 10. Okay, so if we want to get into notation here, it's going to be less than 10, but you can use the 1 there. Okay, and then we'll have times some power of 10. Okay, so what this means is that we're going to take 2.3 times 10 to the 5th power is a 1 followed by 5 zeros, 100,000. Okay, and this will move the decimal point 5 places, the same number of places that's in the power of 10, the same number of places as there are zeros in the number that we're multiplying by. So 1, 2, 3, 4, 5. Fill those empty spaces with zeros, put a comma in there, and I'll write it again, 230,000. Okay, so anything to the times 10 to the 5th, so long as this number is between 1 and 10, anything times 10 to the 5th will be in the 100,000s. Okay, anything times 10 to the 4th will be in the 10,000s. Anything times 10 to the 6th will be in the single-digit millions. Okay, so this all, of course, goes back to our place value system. All right, you've got the 1's place, the 10's place, the 100's place, and so on. And at some point, it just makes more sense to write powers of 10 than it does to write out these really big numbers. Okay, here's the 10,000s, the 100,000s, and so on. Okay. So when we're thinking about these really big numbers, one thing that I found helpful to think about this is to look at the structure of our number system. Let's see, let me put this place value in a place where it's easier to see. So, if we're talking about place value, so 1, 10, 100,000, 10,000, 100,000, millions. And then you get the 10 millions, the 100 millions, and then the billions. Okay, so let's see here. So this grouping right here is all thousands. All right, you get the single-digit thousands, the 10,000s, the 100,000s. This group right here, these are all millions. Right, so you get the single-digit millions, the 10 millions, the 100 millions. And notice how this reflects what we see in these first three place values. Single-digit numbers, 10s, 100s. Single-digit thousands, 10,000s, 100,000s. Single-digit millions, 10 millions, 100 millions. And we can extend that into the billions as well. I'll make some space here, and then we'll look at some problems. Let's see here. 10 to the 11th. This is the billions section. And you get single-digit billions, tens of billions, hundreds of billions, and so on. Okay? All right. So that's the basic idea for scientific notation. And this is also, another way to sort of, reinvestigate our place value system. Because typically we just look at each of these individually, but if you think about the way the numbers are named, they really break out into these sections. Okay? All right. Oh, let's look at the negative powers of 10. which are fractions. Okay, let's see here. So now let's put a place value here, put the decimal point here. There's the ones and the tens. But going back this way, you've got tenths, hundredths, thousandths, and again, at some point, it just makes more sense to use powers of 10 than it does to continue writing those numbers with all those zeros. Okay? So, when you've got a power in the denominator, that's considered to be a negative power. Okay? So this is 1 over 10 squared, or 10 to the negative 2. 1 over 10 to the third, 10 to the negative 3, 1 over 10 to the fourth, 10 to the negative fourth, and so on. So if we had a number, let's say, something like this, okay? So we've got 4 zeros, and then this 45. So if we wanted to read this, you know, this is 45 millionths. You can think of it that way. So if we were to write this as scientific notation, well then this would be, let's see, so we've got to move the decimal point backwards so that this number is between 1 and 10. 1, 2, 3, 4, 5 places. So this is going to be 4.5 times 10 to the negative fifth. Okay? So if you had this number, 4.5 times 10 to the negative fifth, then to write it in standard notation, you would move the decimal point 5 places to the left to make the number smaller. 1, 2, 3, 4, 5, puts the decimal point there, and then we fill in the zeros into those empty places. Okay, so that's a basic idea for representing numbers using scientific notation. Let's look at some examples, and hopefully these ideas I've been talking about will make more sense when we have some examples to apply them to. So the idea here in the first group of problems is we want to take these numbers, which are in scientific notation. Number 2, 6.96 times 10 to the 8th power, and we want to write this in standard notation. All right, so, and this is kind of separate. Let's say I'll just solve the problem first. We're going to move the decimal point 8 places to the right. That's going to make this number larger, okay? That's the thing. If you've got a positive power of 10, this moves to the right. Your answer should get big. This number should get bigger. If you've got a negative power of 10, it's going to move to the left, and your number is going to get smaller. So let's see here. 1, 2, 3, 4, 5, 6, 7, 8. Fill in the zeros. And then we'll put some commas in there. So let's see, 696, 6, and there we go. We've got 696 million is this number. Okay. Let's see. All right, let's keep moving with these. Problem 4. 9.292 times 10 to the 7th. So, same process. It's a positive power of 10. So we're going to go to the right. 1, 2, 3, 4, 5, 6, 7 places. Fill in the zeros. And so then we've got what? 92,920,000. Okay? And then in problem 6, we have a negative power of 10 here. 4.5 times 10 to the negative 7th power. So the negative exponent takes us 7 places to the left. 1, 2, 3, 4, 5, 6, 7. Fill in those zeros, and there it is. 1, 2, 3, 4, 5, 6, 45. And, you know, reading these in terms of place value is not that big a deal at this point, but if you wanted to, you could count out your way here, tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths, 10 million. So this is 4,500 millionths. Okay. All right, now on the next page, we've got very large or very small numbers, and we want to express these in scientific notation. So, problem 8, we've got population of the United States recently at 304 million. I think the recent census might put that upwards of 320 or 330 million, but we'll have to wait and see. But anyway, 304 million. So the idea is we want to count how many places would it take to turn this number into something between 1 and 10, right? So here's the decimal point. 1, 2, 3, 4, 5, 6, 7, 8 places. And so this would be 3.04 times 10 to the 8th power. Okay? Now let's look at a couple more. Problem 10 gives us a very small number. Let's see what we've got here. 1, 2, 3, 4 zeros, and then a 5. All right? Okay. So, again, we're going to count how many places do we have to move that decimal point until we get a number that's between 1 and 10. So we go 1, 2, 3, 4, 5 places. So this number in scientific notation would be 5 times 10 to the negative 5th power. Okay? Typically, any number that's smaller than 1 is going to have a negative exponent. Any number that's bigger than 1 is going to have a positive exponent in scientific notation. All right, let's see here. Problem 12, 0.0394. 0394. That's 1 millimeter is equal to 0.0394 inches. And so we would just go 1, 2 places. And that would give us 3.94 times 10 to the negative 2 power. Okay, so that's the first part of the assignment about scientific notation, representing numbers, going back and forth between standard notation and scientific notation. All right, on the last page of this first handout, we've got some problems where we want to order these numbers. So, problem 14, let's see what we've got. 8.5 times 10 to the negative 5th, 8.2 times 10 to the 3rd, 1.3 times 10 to the minus 1, and 6.2 times 10 to the 4th. All right, so the first place I would look in these ordering problems is what power of 10 are we talking about? I would completely ignore these for the moment. We can look at those afterwards. But it's sort of like those ordering problems that we had on the midterm, where the first thing you want to look at is the biggest place value. You can worry about the other place values later, but this is essentially the same idea. Okay, so the smallest number is going to have a negative exponent. And the bigger that negative exponent, the more negative that exponent is, the smaller the number is going to be. So this is the smallest number right here. 8.5 times 10 to the negative 5th. Okay, next, this is the only other negative exponent, so it must be the next largest number. Okay, it's bigger than this one, but it's smaller than anything that has a positive exponent with the 10. Okay, now we're looking at the positive exponents, right? The bigger the positive number is, the bigger the positive exponent is, the bigger that number is going to be. So this is the biggest one right here, so this one comes next, 8.2 times 10 to the 3rd, and then the biggest number, 6.2 times 10 to the 4th. Now this example didn't have any powers that were the same. Let's see if any of your other examples do. In problem 13, I'm not going to do the whole problem, but in problem 13 you've got something like 2.8 times 10 to the negative 5th and 9.8 times 10 to the negative 5th. So at that point you can just compare this part. Okay, so these are the same. All you have to do is compare these numbers. This one's smaller, this one's bigger. Okay, I think the smallest number in number 13, you should look for, there's going to be a higher negative exponent in that one that will start the answer to problem 13 out. Okay, so that's the first handout on scientific notation, just about representing numbers using scientific notation, and then ordering, being able to put those numbers in order. The next assignment, we've got some calculation problems using scientific notation. I think most of these, I would recommend using the calculator, getting comfortable using your calculator for scientific notation. On this one, to do scientific notation, there's this little EE key. Let me show you where it is on here in case you're using one of these. So you can see right above the 7 there's that comma key, and then in blue above that is double E. So let's see, I haven't got any numbers on the board right now. Let me put an example problem up and then I'll show you on the calculator again. So problem 2. 9 times 10 to the 6th, 5 times 10 to the 5th. Okay, so on the calculator, if I wanted to enter one of these numbers, let's see, let's find the button we need is right there above the 7. So on these calculators, to access those blue colored features, you have to hit the blue second key. So first we type in the 9, okay, and then we hit the blue key and then that E function, and then the power of 10, just the 6, okay. So on the calculator it looks like 9E6, and then we hit times, and what we're multiplying it by is going to be 5E5. And then we hit equals, and there's our answer, 4.5 times 10 to the 12th power. Now, your calculator may work a little bit differently from this one, but they typically work in a similar way. And I do ask that you use the standard scientific notation, which involves times 10 to a power, rather than the calculator notation, this 9E6 times 5E5. Okay? That's fine if you're using a calculator, but if you're going to write an answer down, please use the standard scientific notation. So the other thing I was going to say is that if your calculator works a little bit differently, if you've got a calculator manual, you can look it up. You can search online for some information about how to do scientific notation on your calculator, or just ask me. You know, I've worked with people who have different calculators in the past, and it's usually pretty straightforward to find how the calculator represents scientific notation. Now, just as an aside, if you're interested in how this works, you can multiply the 9 and the 5 to get 45. Add your exponents, 10 to the 11th power. So 45 times 10 to the 11th is the same as 4.5 times 10 to the 12th. That's the same number. See, this decimal point only has to go 11 places. If we put the decimal point here, it has to go 12 places. But this is not standard scientific notation, right? Because that 45 is not between 1 and 10. Okay? All right. Let's look at a few more of these. see what else we've got. Problem 4. We've got 7.1 times 10 to the 5th, and then 2 times 10 to the negative 8th. Okay, so I'll do the same thing on this. I'll do this one on the calculator. 7.1 E5 times 2E minus 8. And it's important to get that negative sign in there. So my calculator comes out with an answer of 0.0142. Now, I could force the calculator to return answers in scientific notation, but to me, that's every bit as much trouble as it is to learn how to do it yourself, okay? We've got to move this decimal point until the number is between 1 and 10. We had to move it 2 places. So this is 1.42 times 10 to the negative 2 power, okay? Now, if we do this without the calculator, do the same thing, multiply the 2 times the 7.1, 14.2. 5 and minus 8 make minus 3. Okay? Similar thing we ran into in problem 2. We only have to go 2 places here, but we would have to go 3 places there to get to that 0.0142. So, this is our answer. And again, if you get an answer like this, please remember to express it in scientific notation. All right, we'll look at 1 or 2 more of these, and then we'll look at the dividing problems. Let's see here. Yeah, let's just look at number 12. Here we've got 8.4 times 10 to the minus 6. Yeah. And 7.3 times 10 to the minus 8. All right, so let's go ahead and put it in the calculator. 8.4 e minus 6 times 7.3 e minus 8. And that gives me 6.132 times 10 to the minus 13th power. Okay, so that's the multiplying of numbers in scientific notation. On the next page, we've got some problems about dividing numbers in scientific notation. Okay, so problem 14. We start out with 9.6 times 10 to the 20th power over 3 times 10 to the 6th power. So again, I'll start out using the calculator. 9.6e20 divided by 3e6. And that's going to give us 3.2 times 10 to the 14th power. Okay? To do this without the calculator, divide the 3 into the 9.6. That's where we get the 3.2. And subtract the 6 from the 20. That's how we get 10 to the 14th power. Number 16, we've got 8 times 10 to the 12th over 4 times 10 to the minus 3. So again, if we do this on the calculator, 8e12 divided by 4e minus 3 gives me 2 times 10 to the 15th power. And again, without the calculator, you go 4 into 8 goes 2 times. And you have to subtract. So we did 20 minus 6 to get the 14. Here we do 12 minus negative 3. That's how we get the 15th power, 10 to the 15th power. Because when you subtract a negative, you end up adding these two numbers, 12 plus 3. Okay. Let's see, let's look at problem 18. .5 times 10 to the minus 8th over 9 times minus fourth. All right, so first we'll do it on the calculator. 4.5 e minus 8 divided by 9 e minus 4. That gives me 5 times 10 to the minus fifth. Now this is a little bit trickier to do without the calculator. One thing you can recognize is that this is 1/2, right? 4.5 times 2 is 9. So this is equivalent to 1/2. So we can call that 0.5. And then we've got to do minus 8 minus negative 4. And that's going to be negative 4. But again, this is not scientific, this is not standard scientific notation because this number right here is not between 1 and 10. Okay? So notice that if you go 4, if you move that decimal, if you move this decimal place 4 places to the left, it's the same as if you moved this decimal point 5 places to the left. Okay? Alright. Now let's look at these problems that are on the last page. Or in the next page of this second handout. And here we've got some combined multiplying and dividing. So let's take a look at it. Problem 24. We've got 8 times 10 to the 4th times 5 times 10 to the 10th. And then on the bottom, 2 times 10 to the 7th. All right, so I'll go ahead and put it in the calculator. And let's see here. 8e4 times 5e10. And then we want to divide by 2e7. And I'll show you what that looks like on the calculator here. And there it is. So 8 times 10 to the 4th times 5 times 10 to the 10th divided by 2 times 10 to the 7th. And what do we get there? Oh, well, let me show you this. So here's the problem, very common to run into this. My answer is not in scientific notation. All right, well, I'll write it down and then I'll turn it into scientific notation. I mean, one of the benefits of scientific notation is that to write this down, I've got to be careful about how many zeros are there. Let's see. 2, 4, 6, 7, 8. Okay. 4, 5, 6, 7, 8. So that's how many places we have to go. 1, 2, 3, 4, 5, 6, 7, 8 places. So that's 2 times 10 to the 8th power. If we were to do this without the calculator, let's see, we could get 40 times 10 to the 14th, 2 times 10 to the 7th, divide that in there. This would be 20 times 10 to the 7th, same thing as 2 times 10 to the 8th. All right, let's see. I'll do one more of these. Problem 26. So 7 times 10 to the 6th, 4 times 10 to the minus 4th, and on the bottom, 1.4 times 10 to the minus 3. So let's go ahead and enter this. 7e6 times 4e minus 4. Divided by 1.4 e minus 3. And again, I get something very similar to this. Let's see how many zeros. 2, 4, 6. So this time 6 zeros. Okay. And so we'd have to move the decimal point 1, 2, 3, 4, 5, 6 places. So this is 2 times 10 to the 6th power. Now, if we do this without the calculator, what do we get? 28 times 10 to the 2nd, 1.4 times 10 to the negative 3. Now 14 into 28 goes 2 times. So 1.4 into 28 will go 20 times, and then that'll be times 10 to the 5th power. Again, same thing as 2 times 10 to the 6th, 20 times 10 to the 5th. But this is scientific notation, and this is not, okay, or not standard scientific notation. All right, so now let's take a look at these word problems. So in these, really the decision about calculation, do we add, subtract, multiply, or divide, that's the decision that you're going to have to make based on what the problem asks you about. So let's take a look at the even ones on here. Problem 2, Neptune is 5 times 10 to the 4th kilometers in diameter. Mars is 7 times 10 to the 3rd kilometers in diameter. Which of the following statements is accurate? Diameter of Neptune is more than 7 times greater than the diameter of Mars. Okay, well it is bigger. Whether or not it's 7 times bigger or not, that we'd have to calculate it. Diameter of Mars is more than 7 times greater. Okay. Choice C, diameter of Neptune. Oh, diameter of Mars is 7 times greater than Neptune. Well, that one's not true, because the diameter of Mars is smaller, right? If you look at the powers of 10, you can see diameter of Neptune is clearly bigger than the diameter of Mars. So choice B is definitely not right. Diameter of Neptune is about 1.4 times greater than the diameter of Mars. Well, we can make a calculation to decide that. And then choice D, again, is saying diameter of Mars is bigger. So B and D are not correct. The question is, how many times bigger is the diameter of Neptune than the diameter of Mars? Okay? Well, if you already know what calculation to make, then you can go ahead and make it. But what I'm going to say about this is, like, if one was 5 and the other was 10, you can see this one is 2 times bigger. And the way to figure that out in something that's not as obvious is to divide this one by this one. So that's what we're going to do. We're going to divide the diameter of Neptune by the diameter of Mars. 5e4 divided by 7e3. And we get about 7.14 times bigger. Neptune is about 7.14 times bigger, and that's choice A. Okay. Problem 4. Head of a pin has a diameter of 1 times 10 to the minus 4th meters. And a bacterium has a diameter, of 5 times 10 to the minus 7th. How many bacteria that size would fit across the diameter of the pinhead? So we've got a pin here, and we've got these little bacteria things that are clearly smaller, right? This is a higher negative number, so this is a much smaller thing. And the question is, how many of them will fit? Again, this is a division problem. You need to divide the diameter of the pin by how big each bacterium is to find out how many of them would fit. So, what are we going to get here? It's going to be 2 times what? 10 to the second, so 200. Let's see. 1e minus 4 divided by 5e minus 7, 200. There we go. Yeah, I think that's what I said. Okay, and this one is not necessarily about scientific notation. Answering this as 200, that's fine. I mean, if you want to make it scientific notation, it's 2 times 10 to the second. let's see. Problem 6. The speed of light, 6.71 times 10 to the 8th power. Scientists use c for the speed of light. Where are we? There we go. How many miles will light travel in 1 minute? Okay. So this is in miles per hour. So you've got a little, we're back to the conversion of units again, or the dimensional analysis, right? So this is how far it travels in an hour. In 1 minute, we'd have to divide this by 60, right? So 6.71 E8 divided by 60. So let's see, this number would be, I think, best written in scientific notation, 83333. We can put the 0.33 on there if we want. So we would round this off, let's call it 11. Oh, well, actually I can't. I got to make that number smaller than 10, don't I? So let's go 1, 2, 3, 4, 5, 6, 7. So 1.12 times 10 to the 7th power. Okay? All right, let's see, what else? If it takes light 8.3 minutes to reach the Earth from the Sun, how far is the Earth from the Sun? Well, this is miles per minute. And let's see, how many minutes does it take for light to reach the Earth? 8.3 minutes. So we've got to take this and multiply it by 8.3. All right, 1.12 E7 times 8.3. And again, I'm getting an answer that's not in scientific notation. Looks like 4 zeros there. 2, 3, 4. Okay. So this is going to be 1, 2, 3, 4, 5, 6, 7. 9.3 times 10 to the 7th power miles from the Earth to the Sun. Or, as we learned in school at some point, 93 million miles, right? Okay. And you can see in moving from standard notation into scientific notation, I did some rounding. We lost a little bit of accuracy, but you know how the science frequently uses this idea of significant figures, and so they tend to do a lot of rounding themselves, and so that's fine. It always depends on if you're in a an educational setting, what the instructor is looking for. If you're in a professional setting, you need to know, well, what's my margin of error, okay? And that can tell you where you need to round, okay? If it's important for you to have a lot of accuracy, then you're going to need to hold on to all those digits and not round things off. But at a certain point, if you've got a glass of water, rounding it to the nearest hundredth of an ounce is really not going to be that meaningful, okay? All right, let's look at a couple more of these word problems. 6. Problem 8. State of Colorado. 1.04 times 10 to the 5th. 10 to the 5th square miles. Okay. Indian Ocean is 2.808 times 10 to the 7th square miles. How many times bigger than Colorado is the Indian Ocean? This how many times bigger question, it's always divide. Divide the bigger one by the smaller one. That'll tell us how many times bigger the big one is. So, 2.808 E7 divided by 1.04 E5. 270 times bigger. Okay. Problem 10, total of all healthcare costs in the United States in 2003 was 1.7 times 10 to the 12th dollars. The U.S. population that year, 2.9 times 10 to the 8th. Okay, so that's about 290 million. You can see our population has grown since then. What was the average amount spent per person on healthcare that year? That word per, remember when we were doing our dimensional analysis and conversion stuff? That word per means divide. So if it's per person, that means you want to divide the amount by the number of people. Okay, so let's go ahead and do that. 1.7 E12 divided by 2.9 E8, and it's about $6,000. $5,862.07. And again, you know, that issue of rounding comes in, depends on what we're using this number for. You know, whether it's 6 or 7 cents, I'm not sure that that's important. But the getting an accurate answer and then thinking about what we need it for is important. Okay, so that's it for these assignments. We'll have one more assignment going forward. And next week we'll look at some dimensional analysis and unit conversion applied to healthcare problems specifically. I think that those are kind of fun. So, as always, if you have any questions on this stuff on scientific notation, if you get stuck with your calculator, please let me know. Thanks.